gravity is a universal force that acts between any two entities. Okay, it actually also works between any two sources of energy, not only mass. And that's in general relativity, but in classical physics we usually talk only about not energy sources and how they interact gravitationally, but matter and how it interacts gravitationally. Okay, so we have a piece of matter here and a piece of matter here. They interact with each other, as opposed to the case where you have electrical repulsion and attraction, like electrons and protons. With gravity, you have only attraction. So any two things attract each other. What that means is this chalk and this brush are attracting each other right now. Why don't they move towards each other? Or do they move towards each other? The answer is that this chalk and my hand are also attracted to each other, and this chalk and the table attract to each other, and this chalk and everything else is attracted to each other, and this brush is attracted to this, etc. Everything is pulling on everything else. Obviously, this is balanced by that, and this is balanced, roughly speaking, it's all kind of balanced out, and the sum of the forces comes out roughly zero. Which force doesn't balance out? The mass of the Earth, which is too big. There's nothing above us that balances it out. Nothing close enough. Okay? Now, let's see if we can construct, and I think we did this one of the first classes, let's see if we can construct the law of gravitation, and that's done in the notes, in those pages that I mentioned before. What would you say ought to be the form of the force of gravity? Okay, the force of gravity, we'll write over here, we're doing now, trying to figure out what's the law of gravity. What should it depend on? Just from your intuition, experience, and so on. What factors should be in there? The color of the object, no. The shape of the object, not necessarily, etc., etc. What things ought to be in there? What should it be a function of? Of the mass. Let's say which mass? Pardon me? Well, if you have two objects, is which mass counts? Only the bigger one? Both of them. Okay, so we have, let's say we'll make a big M and a small m. Anything else? What other factor might have to be taken into account if you're talking about the gravitational interaction of these two masses?
The distance between.
The distance between them. Okay. It turns out that there's nothing else. There are some constants, but functionally this is the only thing. Very simple. How should it depend on this? Which one should be on the top and which one's on the bottom?
Mass is gotta be on the top.
Mass has got to be on the top. Something to do with the mass on the top.
Distance on the
Distance got to be on the bottom. The greater the distance, the less the force. Okay. Now, what should be over here? N plus M? Let's say you add two masses. What do you do to them? Subtract them? Okay. Now, this is what's in the notes. If you have, let's say, one particle here and one particle here, they attract each other. Let's call this one link worth of attraction. If you have two particles here, then these attract each other. This attracts each other also, but we're talking about the attraction of this to this group to this group. So there's two links. If there's three links. So there's 3 times as much gravitational attraction here as there was when there's only 1 and 1. Because there's each one of these 3 is pulling to the other one. So there's, in terms of the interaction between them, not which one pulls which one, but the interaction between the two, there's 3 times as much. How about if you have another one here? What happens? How many links will you have now? 6. Right? So what's the formula for how many links there are dependent on, as a function of how many particles there are? Multiply, it's 3 times 2. Okay, if I had 4, each one that I add links to each one of these. So for every one here, there's an additional 2. Because it just multiplied by 2. For every one here, there's an additional 4. So it's multiplied by 4, right? So you can multiply one by the other. All right? So the formula is, you would expect it to be m times n. The amount of particles of mass in one times the amount of particles of mass in the other, because each one will link to the other. So the total amount of gravitational pull between this and this, two objects, this chalk and this chalk, depends on the amount of particles of mass in here and the amount of particles of mass here, assuming those equal particles, say chalk atoms. The amount of chalk atoms in here, the amount of chalk or molecules in here, that gives you the amount of links. Okay? So the n times n, not n plus n or n minus n and so on, over r. Now, there's a good reason why it's actually over r squared. I'm not going to go into that now, we'll go into it another time. You can see that for various reasons. All right? So the formula is basically m times m over r squared. This r was from the center of the Earth to the object. Okay, we didn't really learn why. Okay, we just took it on faith in the meantime. We see that it's absurd if it would be the distance between the two objects, because then if I put an object on the Earth, I would say that there's no weight if the distance was 0. If it's on the Earth and the distance between the Earth is 0, so there's no weight. That means an object lying on the Earth has no weight, which is ridiculous. Obviously, it has weight, you have to pick it up. Take force. You feel, if you're an object, you feel you have weight. So it's clearly not that. Also, we can experimentally determine that the weight difference of a person on the 10th floor and the 5th floor and the 1st floor in the basement is it's just, you know, unless you have a really extremely fine precision scale, you're not going to see any difference. So obviously, it's not that height which determines the weight, okay, which goes into this equation. But it turns out it's the center of the Earth. So if it's the center of the Earth to the 1st floor, it's r plus, let's say, 10 feet. If it's to the 2nd floor, it's r plus 20 feet. If it's to the 3rd floor, it's r plus 30 feet. So why do we neglect this piece? Why do we neglect this? It could be 10, 20, 30, it could be 100. It's 10 times as much. How can we ignore it? Why not? That's the question. Why does it not influence?
The Earth is too big.
Because this is so big, just like here, we didn't care if this is 2.01 or 2 because it's a difference of only 0.5%. This is 4,000 miles, okay, up to the surface of the Earth. 4,000 miles plus 10 feet, or 100 feet, or 1,000 feet, or a mile is not going to really matter much in most calculations. All right? Now, if you want to get an exact determination and you're very precise, then it will matter. If you're on the top of a mountain, if you're in the Himalayas and you're a few miles up, all right, then maybe you do have to take this into account if you want a really precise measurement. Although the difference is still minuscule. 4,000 miles plus 4 miles, you know, not a very big difference. Okay? What might make a difference is if you're on a big mountain on the Earth, all right, there's more mass here. If you're here, you're affected by the mass of the Earth, and you're also affected by the mass of the mountain. Okay, so you're higher up, so you're further away from the Earth, so there's less gravity, but there's more gravity also because of the mountain. Somebody had a question?
How about if you're on the moon? Same thing?
Okay, if you're on the moon, so this is the mass of the moon times your mass over the square of the distance between the center of the moon and you.
But it'll influence the moon since the moon is smaller.
What?
The moon is smaller.
Yeah, the moon is smaller, this mass is smaller, and this is also smaller. The radius is smaller. Okay, this is smaller and this is smaller, so we'll give you the same answer. We have to plug in and see what the numbers are. This one goes as the square, and this one... Okay. They actually do something like that, whatever. I think one of the problems in the book has to do with the moon, or one of the planets. Okay, it turns out to be about 1/6. So the acceleration is 1/6. Now, what are the units here? Kilograms, meter squared. Now, are kilograms square over meter square a unit of force? Do the units make sense?
No.
Why not? It needs to be what? Not from previous experience. I'm just saying, like, could it be or couldn't it? Well, we don't know. But what are the units of force? Is there any other way that we know of measuring the units of force? We have another equation which tells us something about force. Which equation? F is equal to ma. Right? In the end, we're going to stick this into the F is equal to ma equation. Right? So these units are going to have to match these units. Units of ma. What are the units of ma? Kilograms, meters per second squared. So this is kilograms squared per meter squared. Something's missing. The answer is there's a certain constant here that has those units. In other words, the amount and the units have to be adjusted for that matching. But all you have to do is add this number to any two particles in the universe, and this equation comes out right. So now the equation is basically this. In order to make everything match out in amount and units, because you're comparing, here you're comparing force attractions between things, and here you're comparing a mass times an acceleration. So in order to make it match, you have to adjust the amount in units. But it's a universal amount. It's not like each time you adjust it differently, which makes the whole thing nonsense. The formula is correct, and you multiply by a certain universal gravitational constant, and then you can use it between any two particles anywhere in the universe, or any 100 or 1,000 or 1,000,000 particles or any objects. Okay, we're going to do that. We have the force of gravity between the sun of mass m and, let's say, s, and mass of the earth, me, over r squared, where r is what? R is the distance between the sun and the earth. The orbit, okay, so r sun earth, let's say.